This lecture will discuss the concept of specific heat as well as some associated calculations with it. What we'll be looking at is a definition, a conceptual example of specific heat, so a way to understand it without the calculations, and then of course after that we will look at calculations and how to solve for various aspects of the heat transfer formula. So first, specific heat as a definition, it's an ability to absorb heat from surroundings without increasing the temperature, or it's a measurement of how much heat can be absorbed related to a temperature increase. So this is in a way a bit of an identity for substances, because different substances have different specific heats, or they have different abilities to absorb the same amount of heat, but they'll have different temperature changes. So what that means is within the substance itself, with the way the nuclei are arranged or the chemical bonds are, a certain amount of heat will be absorbed into it, and the temperature may or may not change. Different substances will have different temperature changes. The symbol here for specific heat is a C, a lowercase c, and you'll sometimes see it as C sub P because it is a pressure-dependent substance, or pressure-dependent property. Now in general, when you have a higher specific heat value, that means that more energy gets absorbed without the accompanying temperature increase. If you have a lower specific heat, that means that less energy is absorbed for a certain temperature change. Now, strictly speaking, or I guess not strictly speaking, it's a measure of how well a substance can hold on to energy without the temperature increasing. A formal definition of specific heat would be the amount of energy necessary to raise 1 gram of the substance by 1 degree Celsius or 1 Kelvin. And so we'll be looking at some examples of this. First, here's a hot sunny day in Ventura, California. Many of you may have been on the beach, and if you walk barefoot, you'll know that the temperature of the sand is super hot, right? So it like burns the bottom of your feet when you walk through that sand for the first time. But then the same day, same sun, same time of day, you go straight from the sand into the water, and the water's really cold. So how could that be? Where the sand, the temperature of the sand has gotten so hot, but the temperature of the water has barely changed at all. Well, if the same amount of heat is absorbed and there's a different temperature change, that means that they have different specific heats. And it turns out that they do. Water has a very, very high specific heat. So that number, 4.18, and here's what that means. Water can absorb 4.18 joules that'll raise 1 gram of water by 1 Kelvin. So 4.18 joules. So in order to raise 1 gram of water by 1 Kelvin, it has to absorb 4.18 joules. To contrast that, an estimate for sand specific heat is 0.8. So to raise 1 gram of sand by 1 Kelvin, you only need to supply 0.8 joules. So you can see that's a huge difference. What would that be? A little bit over 5 times higher for water compared to sand. So that's why sand seems so much hotter compared to water, even though it's the same energy on the same day. Sand has a certain property that it doesn't hold on to heat very well. Its temperature will just skyrocket, even with very little energy being supplied to it. So again, this specific heat, it's a measure of a certain substance's ability to absorb heat, and different substances have different values for specific heat, and so it's a measurement of both. And so there's some associated math here, and if you remember the units for specific heat, it's joules, or calories is another unit of energy, so either one, per gram times degrees Celsius or Kelvin. So Celsius here could be replaced with Kelvin without changing the value. So it's energy per gram degrees Celsius, And so that leads to a formula here for how to calculate specific heat. Q is a measurement of heat or energy, and that's one thing to pay attention to here. We have heat or energy, that's Q, and then specific heat is C. Those two get confused a little bit, so you want to watch out for that. C is a constant for every substance. Q can change based on how much energy is supplied. So anyway, the specific heat is equal to energy or heat divided by mass times the change in temperature. So again, Q is the heat or energy absorbed. The units on that could be joules or calories. M represents the mass of a substance in units of grams. And then delta T is the change in temperature. So delta meaning change. The units on temperature could be degrees Celsius or Kelvin. Now to find delta T, you need the final temperature minus the initial temperature, so TF minus T initial. So when you're given a problem, you'll have to read it for which is given as the final and which is given as the initial temperature. And so this formula here, there's 1, 2, 3, 4 different pieces, although I guess you could take delta T and break it up, so there'd be like 5 different pieces. You're going to be given 4 of them and asked to find the 5th. Now sometimes you're going to be given the substance and then say some of these and asked for the other one. If you're given the substance, that is a way of giving you specific heat, because specific heat is, well, specific to each substance. So sometimes that can be a little bit tricky where you're given the substance, not the number for C, so you got to look it up. And those are in a lot of different reference tables. So, sample problem here. Here's one, and so there's a bunch of information there, and so what you got to do is sort through it. 85 grams of a copper alloy, and alloy is just a mixture of different types of metal, so there's probably copper with maybe some zinc thrown in there, some nickel, some other type of metal. It's heated from 30 degrees C to 45 degrees C, and so you can see from this to this, this is your initial temperature, and then this is your final temperature. And it absorbed 523 joules of energy as heat. So what is the specific heat of the copper alloy? So here is our holding tank. Notice we've got all the different setups here. You're asked to find C. Here's what you're given in the problem. Q is 523. So remember, heat and specific heat are often confused. Heat, just joules by itself, is going to be Q. If you're given a specific heat value with these complex units, that's going to be C. The mass of the copper alloy is 85 grams. Final temperature 45, initial temperature 30. Now to find delta, you just subtract final minus initial, so that's going to be 15. So here's your formula again, plugging it in. You plug in your values. Notice the units here. Joules over grams times degrees Celsius. That's going to be the same as joules over grams times Kelvin. It's not going to change the value at all. You actually don't need to do any conversions. I mean, I guess strictly speaking here, you could turn this into Kelvin and this into Kelvin, but your delta is still going to be 15. And so when you do that, you get this specific heat. And that's it. And there you got your units, you're done. So 0.41, that's a pretty low specific heat. Most metals have a pretty low specific heat. That's why they're good for cooking. Next problem here, what mass of liquid water at 25 degrees C can be raised to its boiling point by adding 24 kilojoules of heat? Okay, so in this particular problem, there's a little bit of tricking happening. First, it's asking for mass. So that's a little different than the one we did last. From 25 raised to its boiling point. So the boiling point of water in Celsius is 100. So that's a way that a number can be hidden from you, because you just need to know the boiling point of water is 100 degrees. And by adding 24 kilojoules. So here is your holding tank. You got to think for a minute here. what are we given and what are we asked for? We're asked for mass, and then we need to find the other things. Okay, so first of all, C. Notice this 4.18, it's nowhere in this problem. But what we did tell you was it's water, liquid water. So if you know liquid water, that's the substance, then you can look in a reference table, so there's a bunch of those in your book, they're online anywhere, and get the specific heat. The Q that you're given is 24 kilojoules. Now, this is another thing to watch out for. Notice this unit here, kilojoules, and this unit here, joules. So this needs to be converted to joules, just like this. And putting in your temperature numbers, the final temperature would be 100 degrees because that's the boiling point of water. The initial temperature, 25, gives you 75 C. Now it's time to go to work. Here's your formula. I recommend rearranging it to be in this. This is actually a nice way to start because it's all on one line. It makes it a little bit easier to solve for any other of the problems. So this formula, it's the same as this one, just rearranged. I recommend starting with this one. This is often called the MCAT formula because it MC, that kind of looks like an AT, so MCAT. But anyway, solving for mass, you can get this arrangement. Plugging in your numbers. You got your joules on top, 24 times 10 to the third divided by the specific heat times this, your delta. And if you look closely at your units, they cancel out nicely. Joules will cancel out joules. Degrees Celsius on top here, on the bottom degrees Celsius, those cancel. So the only unit that you're left with here is grams, which is in the denominator of the denominator, which means, of course, that it's in the numerator. And so do all that math and you get 77 grams as your answer. So to recap here, and we'll be doing practice problems in class and we'll be working with specific heat a fair amount, but specific heat measures the ability to absorb heat in its specific to each substance. So you have different numbers for different substances. It's like a little signature. It's a way to identify it. We have a formula here. Q equals M times C times delta T. We did a couple of practice problems with that. And then one little thing to watch out for with these calculations is that they are unit dependent. So you need to make sure that you have all of the units that match each other so that they cancel out properly. So converting from joules to kilojoules or milligrams to grams or whatever it is, they all need to match up and be the same. So that's something to watch out for. And I think that's it for specific heat. And like I said, we'll be doing some practice problems here in class to get a little bit more comfortable with the math.